All right. Hey, everybody. Thank you for joining in on the Marine Institute Graduate Society Seminar Series. We meet every week on Wednesdays at noon. This is being recorded and will be uploaded to our YouTube channel, where you can find almost all of our seminars over the past couple years. Before we do start, I want to provide a land acknowledgement. We respectfully acknowledge the territory in which we gather as the ancestral homelands of the Beothuk, and the island of Newfoundland as the ancestral homelands of the Mi'kmaq and Beothuk. We would also like to recognize the Inuit of Nunatsiavut and Nunatukavut and Inuit of Nitassinan and their ancestors as the original peoples of Labrador. We strive for respectful relationships with all the peoples of this province as we search for collective healing and true reconciliation and honor this beautiful land together. Now, please join us in welcoming Dr. Khanh Nguyen in his talk on changes of the Gilbert Bay cod population after more than 20 years of monitoring. Dr. Nguyen is a fisheries technology expert. We were talking about this before. He received his bachelor's in marine science and fishing technology in Vietnam, his master's in fisheries management in Norway, in Tromsø, and his PhD here at the Marine Institute in 2019. And in a nutshell, you could say Khan's past research has been generally focused on testing new gear technology and comparing it to traditional gear in terms of like size selectivity and catch efficiency and bycatch. Currently, though, Dr. Nguyen is working with Dr. Corey Morris at DFO on understanding the cod population in Labrador's marine protected area, Gilbert Bay. And with that, I'll hand it over to you, Khanh.
Yep. Okay, I see how to share it. Can you see my screen?
Yes.
Okay, perfect. Good afternoon, everybody. Thanks, Colin, for amazing hosting and nicely introducing. The study that I'm going to present today has been done by myself, Dr. Corey Morris, Curtis Pennell, and Dr. John Green. And I am presenting on behalf of the authors. And very happy having Dr. Corey Morris here today, who have been involved in Gilbert Bay MBA almost 30 years, and so he may have helpful discussion in the end. Yes, who I am. Before I've been working at the DFO here in St. John's, I was a PhD student at CSAR Marine Institute, and my PhD thesis focused on the application of artificial light to improve catch efficiency of snow wrap port fisheries. And those are the LED light that I use throughout my study, and it's me. Today I'm going to present something on changes in the Gilbert Bay cod population after more than 20 years of monitoring. And for that, I will firstly, I will briefly summary about the background of Gilbert Bay marine protected areas. I will then present a role of environmental conditions during the early life history of Gilbert Bay cod population. Next, I will compare the lethal and non-lethal sampling methods to estimate age, role, and population size of Gilbert Bay cod. Next, I will present the effect of environmental condition and commercial fisheries outside the MBA on the Gilbert Bay cod population. Finally, I will present technical and management considerations. Gilbert Bay MBA was created in 2005 to protect a local adaptive distinctive population of Atlantic cod and its habitat. The Gilbert Bay MBA located in the southeast coast of Labrador, as you can see in the left map in red square, with a total of approximately 60 square kilometers. The MBA encompasses subarctic yaw inlet with complete bathymetries and several shallow seals. The ice cover the bay surface during the winter from December to May. However, the temperature increased rapidly during the summer, particularly from June to September. And as you can see in the right map, there are 4 zones of the MPA, including zone 1A, zone 1B, known as the Chinese, zone 2 and zone 3. The Chinese is the most important our wintering and spawning area. Interestingly, the Gilbert Bay cod mainly live in the Chinese, live and spawn in the Chinese only. Very little individual were ever found in zone 1A, zone 2, and zone 3. And in order to monitor the environmental factors and biological information, we annually conduct a sample twice a year in the Chinese. And what data we sample? The water temperature data has been continuously collected every 2 hours at different depths and to fixed locations in the Chinese since 1998, as shown in the blue dots in the top figure. Salinity was sampled annually in June and August at different water columns. The air temperature data have been additionally recorded monthly in the Cartwright since 1935. It is big surprise to me that we can obtain the data 400 years ago. And you know, Cartwright is 100 kilometers away from the MPA. And long-term daily river runoff data has been recorded on the Alexis River since 1978 to provide an index of the spring freshet conditions in the Chinese. Keep in mind that the Alexis River does not supply the water for MPA directly as shown in the bottom map. However, it is parallel and is about 10 kilometers away from the Chinese and Gilbert Bay River, which directly supply the water for the MPA. So it's close enough to include the analysis. In order to sample plankton, we use a bamboo nest and conduct annually in June and August. Adult fish have been annually sampled using hand lines in June and August as well. And red dots as shown in the top panel show the handling locations. And most fish greater than 32 centimeters defined as major fish are tagged and released in the same locations. Now I move on the environmental, the role of environmental conditions during the early life histories. Okay. This figure shows the air correlation between 5-10 meter depths inside the MPA and Cartwright air temperatures. We found that surface water temperature is significant correlation to the air temperature in the Cartwright because you know, MPA water temperature data has been recorded since 1998, while Cartwright air temperature has been recorded since 1935. So we can use the air temperature to infer back the MPA water temperature condition in the past if we want to track it. This figure shows characterized air temperature anomaly time series from 1935 to 2018. The anomaly was defined as the temperature at given time, subtract time in the long-term periods, for example, whole data that we have. And blue line here indicates the yearly anomalies, and red line indicates the 5-year anomalies, and dashed line up here and below here indicate one standard deviation. And if anomalies falling in the one standard deviation area is defined as a normal year. Being higher than one standard deviation considered as a warm year, and being lower than one standard deviation is considered as a cold years. We found that air temperature anomalies increase from a negative value to a positive value between 1975 and 2010. As you can see in these periods. However, it's decreased since with 2006 and 2010 being particularly warm. And before 1995, there was a period, 20 years periods with the several colder than a normal year. You can see in this periods. However, years are quite variable with 2010 and being warmest on the record, and 2015 is here being the coldest years within past 20 years. However, 1973, you can see the bottom point here, was the coldest on the record. Top figures of temperatures, hourly temperature in the Fisheries at a different depth between 5 and 25 meters. And bottom figure so the monthly temperature in the Fisheries at different depth. And we found that the water temperatures, the water column temperature is strongly stratified with the depth during spring and summer. Increasingly, as the winter ice melts in May until mid-August, and near surface water temperatures are highest and are most variable compared to deeper depths. The water temperatures in the Fisheries at 5 meters varies between minus 1.5 degrees Celsius in the winter and high as much as 18 degrees Celsius in the summer. And consistently with the air temperature, the water temperature was warmest in 2010 and coldest in 2015. This is complex figure. The figure shows the average weekly discharge for Alexis River from 1978 to 2018 as shown in the black solid line, with sample years indicating the longest effective period on record, as shown in the blue line. This is 2010, and relatively short runoff periods in 2018, as shown in the green light, and dark and light blue shaded area you can see here and here indicates 0.5 and 1 standard deviation respectively, and dashed line up here and down here indicate weekly maximum and minimum discharge, and thick red line on the axis and y-axis represent mean effective periods and water discharge during effective periods respectively. As you can see in the figure, river discharge is low during the winter months from December to March, increase during April with melting snowpack, and then sub-zero again during June, for example, week of 25th. The spring versus March the beginning of the ice free season in the Chinese. This is a period rapidly changing environmental conditions that includes a melting snowpack and increasing estuarine temperature and stratification that corresponds with the spawning time and location of Gilbert Bay cod. Again, this is a really complex figure, but I really like it. The figure shows the relationship between passive periods, density, and depth of cod as hatching time, juvenile length, and density. The black bar you can see here indicate the start and end of passive each spring, and red square here indicate its peak timing. A blue circle here indicate cod as sample during spawning, and the color gradient represent depth of maximum S and concentrations, and the circle size represent density of S samples. The orange dot up here represent predicted hatching time based on temperature dependent analysis of S development and back calculated growth of juveniles, and green dots up top here represent juvenile represent sample juveniles. The color gradient represent average size of sample fish, and size of each circle represent the density. We found that mostly Taiwan X was sampled during early June sampling, 8 to 25 days after peak of spring passive, and cod as dependent is temperature. Cod as development is temperature dependent, which 80% hatch once temperature cumulative degree reaches 90 degrees. The estimated hatching periods from June 11 to July 17 occur near the end of passive periods every year. Based on development rates and back calculated hatching days from the size distribution of pelagic juvenile sample in August spawning concluded each year prior to the end of passive, and no eggs were ever found in the water column during early August sampling. The range in fish length sample in August is in part influenced by the growth periods determined by the timing of spring conditions and hatching days, and subsequent variability in water temperature, and cumulative degree days during June and July has had a positive relationship with length of juvenile. The figure shows depth of X in the water column relative to salinity as shown in the left panel, and temperature as shown in the right panel in early June. The black dot you can see here, and indicate a mean depth of maximum S density sample relative to salinity and temperatures. Maximum concentrations of X was just below strong surface thickener life at a mean temperature of 0.8 degrees Celsius and mean salinity of 25.3 parts per thousand, and at the depth typically greater than 5 meters. X was generally below the thickener life, as I just said. However, during years when river discharge was low, for example, 2010, 2012, and 2018, X was sample near the surface at the depth of 2 meters. This is not surprise, you know, the cod as are buoyant at the given water density. And now I move on a comparison of lethal and non-lethal methods to estimate a growth rate and population size of an endemic bay population of Atlantic cod. Biological information such as growth rate is a primary input indice of the stock assessment model and the basis of stock assessment. Lethal sampling methods stop in 2009 because of avoiding the negative effects of small populations. And non-lethal sampling methods, including mark recapture, length frequency data, continuously conducted from 1998 to 2019. Actually, as I said, we annually collect the data, but for this analysis, we focus on that period. And the question is whether lethal and non-lethal sampling methods provide sufficient information to manage the small endemic bay cod populations. We use growth rate parameter estimates based on the one battalion fee growth model as shown in the equation, and this is very common and widely wide methods has been accepted and used. This table shows the comparison of growth rate parameter using lethal data based on otolith information and non-lethal sampling data based on mark recapture and length frequency data. You don't need to care about a specific value here. However, there are some points that you might want to know. We found that the lethal sampling method and non-lethal sampling methods provide consistent growth rate parameter. You can see in the right figure for visual comparison. Growth rate curves are really similar for three data. However, there are some advantages and disadvantages for each the methods, each of the methods compared in this study. For example, mark recapture data methods requires a large and consistent marking and recapture program to have confidence in population estimates, which sometimes really hard to maintain. And length frequency methods requires the sampling of a fish from each age category, which is sometimes difficult to, particularly if our fish population have low abundances of several older or younger classes. The figure shows growth rate curve of Gilbert Bay cod from 1998 to 2009, as shown in the top panel, defined as a high abundant level period. And from 2010 to 2019, as shown in the bottom figure, and defined as low abundant periods using electronic length frequency analysis, not elephant, or elephant without trunk. Well, actually, this method has been developed by FAO in early 1980s, but recently it's developed in a package. It's very helpful and useful for our people. The model so that length frequency data analysis using elephant based on one battalion fee grow parameter resource similarly to mark recapture analysis for both barriers. And we found that fish grew faster during high abundant periods than low abundant periods. This is contrary with what we thought. We assume that fish grew faster recently because there are more food when cod abundance is low. Unfortunately, the result is opposite. Top figure shows winter, annual, and summer growth rates of Gilbert Bay cod based on mark and recapture length measurements for different size groups, imagers, margarine, and major group. Bottom figure show frequency of fish captured at different distances from the release location for different liberty times. We found that Gilbert Bay cod grow rapidly during the warm summer months, but have negligible growth during 6 months of winter. This is different from other populations. For example, offshore cod population, which grow continuously around a year. Expectedly, immature fish grow fastest, followed by margarine and major fish. This makes sense because children grow faster than adults. Gilbert Bay cod are strong size fidelity animals. As you can see in the bottom figure, most fish were recaptured as the release size. The sonic tracking indicated that some adults migrate outside the MBA boundaries in the summer between July and August and return to the Chinese and overwinter until next year. This creates the high fish to commercial fishing. This figure shows length frequency distribution of Gilbert Bay cod capture by hand lines in the Chinese from 1998 to 2019. Vertical black lines indicate mean length of cod for a given year. Keep in mind that although the Oceans Act MPA was created in 2005, fishery restrictions were in place before. We found that the CBUE of Gilbert Bay cod significantly decreased from almost 6 to 0.09 fish per rod hour during the observation period. Mean length of fish caught also decreased from greater than 40 centimeters before 2007 to about 30 centimeters after that, as you can see in the black vertical line for those periods. This table shows the estimations of mortality rate, exploitation rate, and biological reference points from the Gilbert Bay cod from 1998 to 2019. Again, don't care about the specific value, but some points I need to present here. Fishing mortality rate of Gilbert Bay cod ranging between 0.18 and 0.59 per year is substantially higher than the natural mortality rate, which runs between 0.06 and 0.14 per year. This is consistent with sonic tracking monitoring. And fishing mortality was higher than the maximum sustainable yield in all years from 1999 to 2019, except for a few years, for example, 2000, 2001, 2005, ranging between 0.15 to 0.65. This figure shows estimates the population size based on different data. The green bars indicate the population size estimates based on the land frequency data. And blue bars indicate the population size estimates based on sprint mark recapture data, and dark blue bars indicates the population size estimates based on some mark recapture data, and red line indicate biomass. We found that the Gilbert Bay cod population size decreased from almost 40,000 individuals in 1999 to about 7,000 individuals in 2019. Approximately 96% decrease is too bad. The population's biomass decreased from the estimated 35 tons to only 1.4 tons in the same time. A good thing is that the number of fish estimates, estimated from the summer sampling only increased, indicated a slight increase over the study period, as you can see in this change, suggesting non-migratory fish can significantly contribute to the recruitment. And now I move on the effect of environmental condition and commercial fisheries outside the MBA on the Gilbert Bay cod population. Keep in mind that there are no fishing, no removal activities inside ABA, but commercial fishing is still operating along the coast of Labrador, of course, within the home range of the Gilbert Bay cod. So as I said that the population size decreased 96%. So the question is, why does the Gilbert Bay cod population decrease? Which the factor was attributed to these situations? To answer that question, we use the Bayesian model, averaging model, to predict the effect of commercial fisheries and environmental conditions on the variability of sample F and juvenile density and adult abundance. And those are in the table. Those are the 23 variables include the model, including the landing volume, river runoff, information, air temperature, and water temperatures. The table shows top 5 models selected by the BMI describing the variability of cod density. You know, there are a couple hundred parsimonious models, but MBA suggests the best 5 model based on the lowest BIC and highest posterior probability. The model shows that landings and phasic features, for example, timing and volume, could explain variations of X density in different years. And commercial fishing was the most important factor affecting X density variability based on highest posterior probability, as you can see in this column for the posterior probability for each variable. And landings accounted for 89.2% of the variability among 125 model returned, compared to 61% for first day of phasic and 36% for duration of phasic, and 80.5% for maximum days of phasic. The model saw top 5 models selected by the BMI describing the variability of juvenile density. Again, 5 predators, including landings, first day phases, and mean air temperature and cumulative degree date at 3-meter depth could explain the variability of juvenile density. As you can see, the value for those variable in 5 model here. Again, fishery landings had the highest posterior probability with 81.7%. You can see in this column again, and occur in 4 of 5 selected model. This table shows top 5 models selected by the BMA describing the variability of adult cod abundance. Commercial fisheries landings data was the most important predictor that explained variations of sample cod abundance based on the highest posterior probability, for example, 100%. You can see here, landing. Landings as a predictor occur in all 5 models, while other predictors had a very limited contribution. So we conclude that commercial fisheries outside the MBA is attributed to the Gilbert Bay cod population decline. The study conducted by Dr. Morris and Dr. Green and has been published recently. The study showed that when the Gilbert Bay cod population decreased, other species increase. So this resource may explain why Gilbert Bay cod population grew slower during past few years, although low abundant level periods compared to the high abundant periods. And finally, I will present some technical and management measures. The study compare the catch rates of collapsible pods against the gill nest, which traditional use along coast of Labrador. The study found that collapsible pods capture comparable amounts to the traditional gill nest used along the coast of Labrador, which could release a live visual distinguishable Gilbert Bay cod. As you can see in the right pictures, Gilbert Bay cod has the different color from the offshore cod because of the diet. Gilbert Bay cod mainly eat shrimp, so their skin has golden, and they also known as a golden cod. And using pods near the Gilbert Bay MPA would benefit existing conservation efforts to protect a local population of Atlantic cod in Gilbert Bay, helping to meet MPA objective. This study investigated some biological information of Gilbert Bay cod, and the study also suggests some management measures. The study showed that the MPA effectively protects the most important spawning area and many Gilbert Bay cod until sexual maturity, but it fails to protect many larger fish due to fishing outside the MPA. Low level of population can produce strong years class. This is a very important point. Adaptive management is recommended to improve MPA effectiveness and changes the seasonal timing of commercial fishing outside MPA would benefit for the conservation. The study could not be done without great help for many people that I could not list all here. Yes, that's it. Thank you very much. Any questions, comments?
All right, thank you. Yeah, that was great. Yeah, do we have any questions? You can go ahead and raise your hand or type in the chat if you'd like, and we can read it. I was kind of curious. I know that when you do length-based or length frequency stock assessment measurements, the type of sampling equipment you use is really important. Well, I mean, that's the case for anything really when you're doing stock assessment. Does your work with size selectivity in the past help you kind of understand the abilities or the limits of using certain sampling methods, or maybe like how trustworthy they are when it comes to, you know, like how much faith you have in the stock assessment when you're like, oh yeah, but we're probably missing every fish that's, you know, this size or something like that. Do you think that your background has helped you understand that a little bit more?
Well, thank you, Colin. Well, yes, you know, we sample using the hand lines with consistently using jigs. You know, for hand line and long lines, the selectivity curves look like a bell. So it's select for specific length, while the length frequency analysis, I mean the stock assessment based on length frequency analysis required for the larger range of length. However, as you asked me about the background to support for this analysis, yes, yeah, because I've been conduct the statistical analysis on the size selectivity. So it's yes, it's help me somehow to understand, to catch it more easily on the length frequency analysis.
Yeah, for sure. It seems like it would. Yeah, I've done some of that stuff in class, and it took a while to wrap my head around it. And then I was like, oh, okay, I get it. But I assume, yeah, that really helped. Yeah, so from Noel, where did the mortality estimates come from? They seem low, he said. The M estimates.
Here, yeah, we for the possible before 2007, the length, the mean length is also larger and more fish caught. This is standardized figures. So more recently, because of the low population size, so we caught less and less fish recently compared to the years before. It makes sense because of the sample, the stock size decreased really much, as much as 96% SS. That's what you know.
So that I think he means the natural mortality estimates.
Oh, not natural mortality.
Yeah, I think that's what he's talking about.
Okay. So say again what
He said, where did the M estimates come from? They seem low.
Okay. This is based on the length frequency data. This estimates based on length frequency data, and yeah, the models. The model predict that value. Actually, I am not really understand much about the procedures there, but for that method, my understand that the maximum sustainable yields calculated based on the mortality, including fishing mortality and natural mortality rates, and then exploitation rates, and they estimate the maximum sustainable yields. And natural mortality here is really low. It's my sense with the sonic tracking, we found as a dot caught in Gilbert Bay local adaptive. They can live in the extreme condition. So sonic tracking so that the Gilbert Bay Gilbert Bay caught have very low natural mortality compared to fishing mortality, I think.
Okay, yeah, that's neat. I didn't know that. Yeah, and Corey says, thanks, Khanh. What do you want to do next, and where do you go from here?
It's a big question. So keep monitor the population, and we have I think for the management can have some adjust, and you know, the fishing outside the MBA's ISS here is, you know, there are about from 3 to 20, less than 20 fishermen around the coast of Labrador. So I think this might be cheaper with subsidized program like support for fishermen, and ask them to stop fishing for a while, and that might have to recovery stock size in the near futures.
Yeah, good luck with that.
And you know that the benefit from fishing is less than 100,000 a year.
Oh, okay. Well, all right. That seems achievable then. All right. Do we have any more questions? I didn't see any hands. Oh, just close the chat.
I don't see.
All right. Yeah. So I think that's it. I'm going to wrap it up here. Thank you so much for the talk, Khanh. Before I end it, I do want to introduce next week's seminar. On Wednesday, April 6th at noon, we have a stock assessment legend, Dr. Carl Walters from UBC, giving a talk titled The Role of Pinniped Predation on Recent BC Fish Stock Collapses. So a hot topic, you know, sea lions and seals and salmon. So it should be interesting. So I hope to see you all there, and have a great Wednesday. And thank you again, Khanh. That was great.
Thanks.